A new technology for building computers is on the rise. Derived from quantum mechanics, today we will be discussing the properties of quantum computers and what makes them so special when compared to classical computers. We will also be looking at why we should care about this new technology when we already have very powerful supercomputers. But before we begin, hit that subscribe button and become part of the Critically Selected family. Okay, so why should we bother with quantum computers? Let's take a look at Moore's law for some answers. In 1965, Gordon E. Moore, co-founder of Intel, predicted that the number of transistors in a chip will double approximately every 24 months, cutting the cost of computers and other such devices in half. A transistor serves as a switch that can be turned on or off to manipulate the electron flow inside electrical devices such as computers. Chips and transistors are microscopic structures that contain carbon and silicon molecules, which are aligned perfectly to move electricity along the circuit faster. The faster a microchip processes electrical signals, the more efficient a computer becomes. It can be thought of as neurons in a human brain, but in the form of silicon and carbon that is on a computer chip rather than on organic material like our brain. This doubling process makes our computers more powerful than before by shrinking the size of these transistors. Recently, transistors have become so small that they are approaching the size of a single atom. This poses a problem because down at the subatomic scale, laws of physics do not work the same way as they do on larger scales. Phenomenon such as quantum tunneling starts to happen where subatomic particles such as electrons pass through barriers regardless of whether the transistor is on or off. This means that we can no longer make our computers more powerful by shrinking computer chips and transistors and have to find a new strategy to make advancements to our computing power. One solution to this problem is to develop a quantum computer. Quantum theory, also known as quantum physics or quantum mechanics, is a theory in modern physics that deals with the nature of atomic and subatomic particles such as electrons and photons. It incorporates the concepts of quantization of energy, wave-particle duality, the uncertainty principle, and the correspondence principle. In summary, what this means is that energy always comes in integer multiples of some fundamental energy and that all matter in the universe is both a wave and a particle. This is counterintuitive based on our everyday experiences since matter on large scales does not exhibit this dual nature of both waves and particles. Furthermore, we cannot know for certain both the momentum and the location of any given particle since these particles are in an uncertain and non-deterministic probability wave. From these basic principles, two of the most useful ideas emerge that serve as key components of a quantum computer: superposition and quantum entanglement. Superposition allows particles to be in all possible states at once because of the probabilistic nature of these particles. Unlike the macro scale, quantum particles do not need to be in a definite state, which is why they exist in a probability wave function containing all possible states at the same time. This wave function collapses to a single definite state when we try to measure it, however. For example, the spin of electrons or polarization of photons are undefined until they are observed collapsing the wave function to a definite spin or polarization. Furthermore, quantum entanglement allows particles to interact with each other in such a way that knowing the state of one particle will automatically describe the state of the other particle as long as they are entangled. This phenomenon seems to be unbounded by distance, which is why Albert Einstein called it spooky action at a distance. Together, these two concepts are fundamental to quantum computers and, when used appropriately, have the power to revolutionize our computing power in many instances. Now that we have some background knowledge, let's dive right into a quantum computer. A classical computer contains microchips that contain transistors that allow the flow of information in the form of bits. A bit is a binary digit and is the smallest increment of data on a computer. It can hold only one of two values, 0 or 1, corresponding to the electrical values of off or on in a transistor respectively. Combinations of many bits representing a 0 or a 1 are used to store more complex information and compute more complex problems. Since each bit can only be a 0 or 1 at any given instance, solving problems such as optimal routes from point A to point B can consume vast amount of time on a classical computer. A quantum computer, on the other hand, does not use transistors or classical bits. It uses quantum bits or qubits that can represent a 0 or a 1 or both of these states at the same time based on the principle of superposition. It is this property that gives quantum computers the potential to be millions of times faster than even the classical supercomputers of today. For example, suppose we have 2 bits on a classical computer. This means that there are a total of 4 possible configurations out of which we can choose only one. However, 2 qubits in a state of superposition in a quantum computer can be in all 4 configurations at once, making calculations on a quantum computer exponentially faster. As long as the qubit is unobserved, it will be in all possible states, only collapsing to a definite value of 0 or 1 when it is observed, making it a regular classical computer. To counter this problem, scientists make use of another property of quantum mechanics known as entanglement to make measurements indirectly and preserve the system's integrity. So in principle, if an external force is applied to 2 qubits, they can become entangled. Once this happens, measuring the state of one qubit will be enough to deduce the state of the second qubit without having to directly observe it. Combining these two principles, qubits can become an extremely advanced version of switches solving problems which would be impossible to do using a classical supercomputer. In general, given n bits and n qubits, a classical computer can perform 2 to the n operations one by one, whereas a quantum computer can simultaneously perform all 2 to the n operations at once. This means that having only a few hundred qubits will already be faster at problem solving than some of our computers with billions and billions of bits today. So, what kind of problems will a quantum computer solve for us? Quantum computers can be used to solve many unsolved problems. For example, they can be used to accurately model molecular interactions leading to breakthroughs in medicines, as well as solving optimization problems such as finding the best possible route between 2 cities, cutting the cost down tremendously. Accurate weather forecasting and climate change models will also become readily available. Moreover, quantum computers will be able to break very large numbers into their prime factorization, revolutionizing cryptography. In general, quantum computers will be able to solve problems with small inputs and very large outputs due to their special quantum properties. They can even advance our understanding of physics and mathematics by helping to model complex particles and solving very difficult mathematical problems which would be impossible to solve on a classical computer. There you have it. What do you think a quantum computer will be capable of when it is finally commercialized? Will it be able to tackle these difficult problems, or is it all just hype? Let us know in the comments down below. We would love to hear your opinion on this. Also, if you like this video and want to see more stuff like this, give it a thumbs up by pressing the like button. Make sure to subscribe to our channel if you haven't already and click that notification bell so you don't miss any of our future content. Until then, we'll see you in the next one.